Right.
Yeah. Hey, thanks for that introduction, Ahmad. So, my name is Bhaskar Chinni. I'm a product manager at Broadcom. And today I will present this rogue transparent clock detection with my colleague Amit Oren, who is also a distinguished engineer from Broadcom. So the agenda here is, many of you are familiar, but I'll just spend a couple of slides on introducing what is transparent clock. And then we will discuss what is our rogue transparent clock. And then Amit will go over the solution. So transparent clock is basically a mechanism that measures the time it takes within the residence time, right? The residence time of a switch. And in this scheme, unlike a boundary clock, all the endpoints directly communicate with the grandmaster. I mean, the packets will go through hop by hop, but they are essentially talking to the grandmaster. And that kind of brings some simplicity because the messages are not getting terminated at each hop. They are only the correction field is getting updated, and the packets are transparently going from the grandmaster to the endpoint. And there are two types of mechanisms here, right? One step and two step. And in one step, the transmission time is added to the message itself, and there is no need for follow-up. And that means it is kind of stateless. Right? In the two-step mode, there is a follow-up message that will carry the timestamping, and that kind of, you have to maintain some state in that sense. And there are two different types of clocks here within transparent clock. One is end-to-end, and the other is the peer-to-peer. So the one I described just now is called end-to-end transparent clock, where the time measured from endpoint to the grandmaster. Whereas in the peer-to-peer case, like as I'm showing in this slide, right, the TC only measures the switch residence time, right, per each. And then that is how the endpoint will leverage those collective TCs, correction fields, and then it will synchronize with the grandmaster. Whereas with the peer-to-peer delay, it is not only the switch residence time, but also it includes the link delay time. So that's the difference between peer-to-peer. And also, it requires the exchange with the next peer node, not necessarily in the between the grandmaster and the end node. So in that sense, peer-to-peer scales better than the transparent clock. So now that we understand what is a transparent clock, what is rogue transparent clock? So because transparent clock is easier to implement compared to boundary clock, and also it provides good enough time sync performance for many applications, including data center and other applications, it is really taking off, right? And Meta is also has also deployed a transparent clock, and at a large scale. We're talking about hundreds of thousands of switches. When you have these kind of scale and TC deployed, you need some kind of automation to ensure the performance is actually working well, right? Because if you have to manually monitor those many 100,000 nodes and take corrective actions, meaning it is very cumbersome process and sometimes error prone. So what we are doing here now today, this is a very innovative solution. It's actually Amit's brainchild. where he came up with an idea of an automated scheme where with the help of an agent, we will be able to identify how, if a transparent clock is misbehaving, and if so, we can easily determine in an automated manner. And that way, the IT can take corrective action. And that's what we are going to discuss today. So the idea is it has two components. There is a one sync agent that basically runs within the switch, not in the host CPU, not in the network operating system, within the silicon, and it has two actions, right? One is the P delay initiation, and the other is the P delay responder. And the way it works is the switch will send P delay initiation messages to the upstream switch, and then the upstream switch will respond, to the downstream switch. And the delay responder need to respond in a very, very fast manner for this mechanism to work. Otherwise, you will not be able to come up with this right measurements. So with that, I will hand over to Amit, where he will go and explain further details. So Amit, you can take over from here.
Okay. Looking at the rogue PC detection problem, this is essentially from a statistical perspective. This is basically a one-bit classifier, right? It's looking at the measured round-trip time data and has to make a decision on whether it's looking at a rogue TC situation or no rogue TC situation. This is a binary classification problem that, like any classification problem, is characterized by two very important numbers. One is the false positive rate, and the other one is the false negative rate. False positive basically means that we incorrectly classify a peer node as a rogue TC even though it isn't. And the importance of this number is that if we have a very large deployment, like would be the case in a data center where we can have, hundreds of thousands of TCs, if the false positive rate is not carefully controlled, it means that the IT department is chasing false alarms. The false alarm rate is too high, and the detector is not usable, right? That we cannot have a situation where false alarms are too high. If we want to get an idea of what kind of false alarm rate we need, then consider that if I have a single transparent clock that is performing a measurement every second, which means that it has 2.6 million measurements, say, in a month, and I have hundreds of thousands of transparent clocks, then to keep the false alarm rate under control, I need at least 10 to the minus 12, if not lower, false positive rate. That has to be a near zero false alarm rate to make this useful. The other metric, the false negative, essentially is the failure of the detector to detect rogue TC when one exists. And this is also a problem, right? If the detector is, say even 80%, has a detection rate of even 80%, that's not enough that 20% of the rogue TCs are not identified correctly. So the goal here is to make these two numbers both small. It is a well-known fact that these are that making these two numbers small simultaneously is not a This is not possible. In fact, it's well known that attempting to reduce one typically causes the other one to increase. So one comes at the expense of the other, and so one has to make a careful decision of how to tune the detector so that it achieves the false positive rate that we want to make sure that it doesn't generate too many false alarms while making the false negatives or probability of detection as high as possible. So let's move to the next slide. Yeah, so in this is sort of an example that kind of shows the problem that if we look at the blue curve here, and we say this is the distribution of delay measurements when no rogue TC is present, so we get typically smaller delays. And we look at the other curve, the green dashed curve is the distribution of delays when a rogue TC is present, then and we attempt to position a decision threshold. It exemplifies the problem of one coming at the expense of the other, right? If I want to make the false positive rate smaller, and false positive means that I crossed my threshold, so I detected a rogue TC, but we're looking at the area under the blue curve, which means that there is no rogue TC present, but yet I detected one. That is the false positive rate, and if I move the threshold right to make this number small, remember we're looking for something like 10 to the minus 12, then what that means is that the area under the green curve on the left of the threshold, which is the false negative rate, begins to increase, making the detector less and less useful. So that is a typical analysis that demonstrates the problem of these two numbers and how they're related to each other. There is another complicating factor, which, in the interest of time, we'll put it aside, called class imbalance, that basically says that, the a priori probability of even seeing a rogue TC is small to begin with. And that means that the probability of crossing the threshold is dominated by false positives, which, is yet another complicating factor. But fortunately, when we decided to go and measure what is actually going on here in a real scenario, and let's move to the next slide, we basically put together a setup where on the left, we have a situation where there is no rogue TC. We have two transparent clocks that implement peer-to-peer delay measurement between them. And on the right, we have a rogue TC situation where we have a switch that is not a transparent clock between two TC nodes that, again, have peer-to-peer delay measurement running between them. That you can actually see that from this histogram that these two distributions are so well separated that you can actually achieve the goals of near zero false positives and very low false negatives without a lot of difficulty. So if there was ever a scenario where that you have a very low false positive and very high statistical power of the test, this is probably one of them. So that leads us to believe that the performance of this method of TC detection, or rogue TC detection, will perform very well in practice. So any questions?
Yeah, actually, that's the last slide.
Just
you should also note that
in the interest of time,
this method is almost not dependent on the length of the wire between the two TCs. that even if this wire was longer, right, and I had more delay between them, that this whole histogram, all of it, would shift to the right, but the distance between these two distributions would still be high enough to ensure that we can actually do a good job of detection here.
All right. Thank you very much, Amit.
Yeah.
And
Thanks, Amit.
Bhaskar.
Okay.